in this advanced conduction series, and so firstly let us briefly recall what we did in the last lecture. So in the last lecture what we did was we went through the derivation of the thermal energy balance with the second approach, and also I talked about the Fourier's law of conductivity and Fourier's law of thermal conduction, and I told you that how we can get it, and I also told you that it cannot be proved mathematically, but it is an universal law which can be verified experimentally, right? And I showed you that in general the heat flux, the component of heat flux vector in any one direction can be dependent upon the temperature gradient component in other directions. Okay, and the parameter that is correlating the components of the temperature gradient and the component of the heat flux vector, that is nothing but the components of thermal conductivity tensor. So I told you that in general thermal conductivity is a second order tensor, that is a 3 cross 3 matrix, right? And I told you that in this lecture I will be proving that for an isotropic material it boils down to a constant, okay, or a constant into an identity matrix, okay. So to do that I need to take help of the tensor algebra or the use of indicial notation. So first let me briefly talk about that. So today is lecture 5, right? So indicial notation, right? Now we will learn something called uh, laws, or let me say it as a rules of indicial notation. It is also famous in terms of Einstein indices, okay. Rules of indicial notation, and also we will learn some tensor algebra, okay. So this is the topic for today's lecture, okay. So first let me ask you a question, that what is a vector? So you know that a vector is nothing but a parameter, or it is a quantity or anything you can call it, but it has a magnitude and also it has a particular direction, as well as it has to obey the laws of vector addition and multiplication, right? So now if I ask you a simple question, that is how many informations are required to specify a vector, so then you will tell that two informations. And what are those? Those are direction and magnitude. Now I am specifying that without magnitude how many information are you needing, okay. So then it is one, that is any one direction, right? So is there anything that requires two directions to be specified? Is there anything that requires three directions to be specified? Is there anything that is required four directions to be specified? So here the information is basically the number of direction. So the information is the direction. If that is so, then for vector that information is only one, okay. For stress. So stress, to define stress, you have to define the direction of, you have to define the direction of the force as well as the direction of the surface, right? So stress is needing two directions, okay, and we will see that thermal conductivity is also needing two directions. You see here I have shown you that. So let us take any component like K32. So K32 is having two directions. One is corresponding to the direction of the temperature gradient, another is corresponding to the direction of the heat flux vector component. So this index or this subscript 3 is indicating that which heat flux component I am concerned about. This 2 is indicating that which temperature gradient component is being correlated with the heat flux vector component. Okay. Therefore, stress, thermal conductivity, these types of parameters are having the requirement of two informations or two directions to be specified. Okay. Now there are more quantities in solid mechanics. We have the modulus. Okay, so modulus actually in the most general case will have four independent directions to be specified. Okay, so this was the prelude. Now see any vector A. So if A is a vector, okay, then I can write this A as Ax I cap plus Ay j cap plus Az k cap, right? Now I am just drawing the coordinate axis. So this is the I cap direction, this is the j cap direction, and this is the k cap direction. So this is the x coordinate, this is y coordinate, and this is z coordinate. So now what are I cap, j cap and k cap? These are unit vectors having the magnitude 1 and showing the only the directions, right? Now what I am doing here now, that is I am replacing this x notation by x1, okay, by x1, this y notation by x2, z notation by x3. So I am just calling this x as x1, y as x2 and z as x3, okay. And the corresponding unit vectors are in x direction or I cap direction it is E1 cap, in y direction or x2 direction it is E2 cap, and in x3 direction or z direction it is E3 cap. So I am just giving these things some different names, like we also have various names, like, right? So one name is for your home, your friends may be calling you with another name. So this is nothing but the same thing, that is the significance or the basic mathematical properties are not being changed, only the names are being changed, okay, the new names are being given. Now what is the benefit of that? Let us see. So in this notation, that is x1, x2 and x3 and e1, e2, e3, I can write this vector A as a1 e1 cap plus a2 e2 cap plus a3 e3 cap, okay. So this a1 is the x component of the vector A or x1 component, a2 is the x2 component of vector A, a3 is the x3 component of vector A, okay. So now if I say that I have to give another notation for this vector A, so then I can write this as AI. Now this is the beginning of the initial notation. Here this I can take three independent values. Okay, this I can take three independent values. So for I equals to 1, it will be A1 and it will denote x1 component. Okay. For I equals to 2, it will denote A2 and that is nothing but the x2 component. For I equals to 3, it will denote A3 for x3 component. Okay. Now any index that can take three independent values, okay, that is called a free index. Okay. So this is a free index. Okay. So I am writing separately, that is, this is a definition of free index. So that is the index that can take three separate values. Why 3? That is because physically we have only 3 dimensions or 3 directions. So now you can argue that we have 4th dimension as time, right? So we are not considering that in this uh, course, okay, or we are only concerned about the 3D or the space coordinates only. So in terms of the space coordinates, we only have 3 independent directions. That is why it is the fact that the free index is an index that can take 3 separate values or 3 independent values, not separate. I mean, separate is a correct word, but the good word is independent values. Okay. So if I am writing anything like Bi, that means this is a vector. Okay. So it directly means that vector is a parameter that is having one free index. Okay, having one free index. Okay. Now you see that likewise, if I now take the stress, okay, stress, and I denote it by sigma. Okay, or let me call about the, I mean, let me talk about the quantity thermal conductivity K. Now you see that I require K equals, I mean K to be specified 2 independent directions. So I write here K I j. Okay, K I j. So let me just copy this matrix again. Let me copy it here. Okay. So now you see from this one, if I equal to 1 and j equal to 1, I have it is k equal to 1, I mean k11, and k11 is correlating q1 double dash and del T1, that is the x1 component of the temperature gradient. Now if I take I equal to 2, j equal to 1, then I am having k21, and it is correlating q2 double dash and gradient T1. Okay. So you see, each of these indices are free indices. This is a free index, and this is also a free index. Okay. So separately I and j, so let me write it. So I comma j independently, these words are very important, independently can take 3 values. So that directly means that for each value of I, how many values can j take? 3. So for 3 values of I, how many pairs of ij is possible? That is 9. So that is why you see that we have here 9 components here, 9 components for k. Okay. Similarly, if we have something, okay, so I am just calling the actual name, so it is called a permutation tensor. Okay, permutation tensor. Now I have already coined the term tensor, but I will explain it. Okay, just now accept this name permutation tensor, and I will talk separately about this word tensor. So permutation tensor is epsilon ijk. Okay. Now you see that here I have 3 independent indices. Okay. So here this this I, this j and this k, all these are free indices. Okay, all these are free indices. Now you tell me that how many components are possible for this epsilon ijk. That is nothing but 3 into 3 into 3, that is 27. Okay. Now this permutation tensor, as I have already introduced to you, now let me talk about its mathematical properties. So that is epsilon ijk is equal to 1 if I, j, k are in cyclic order. Okay, let me write it separately. Okay, cut, paste. Okay. So what do you mean by cyclic order? That is, if it is epsilon 1 2 3 2 3 1 3 1 2, if it is like that, then it will be 1. It will be minus 1 if I, j, k are not in cyclic order. Cyclic order. Okay, and it will be 0 not in cyclic order, and I not equals to j not equals to k. It will be 0 otherwise. So this condition actually is obeyed in this case also, that is here also I not equal to j not equal to k, because and I have not written in the first condition that I equal to j I mean I not equal to j equal to k. That is because if I is equal to j is equal to k, then they are surely not in the cyclic orders. Cyclic order means I, j and k, they have to be I mean different by definition. Okay. So this is the property of a permutation tensor. But now the main crux of the matter is that is it is having 3 free indices. Likewise, if I talk about something called modulus, okay, so that is denoted by C. Now C I J K L, so it is having 4 free indices. Okay, so how many components it can have separately? That will be 3 to the power 4 equal to 81. Okay. Okay. So now let me introduce the concept of tensor. So so everything that we have already studied, that is maybe Bi, sigma, or okay, Kij, then I have talked about epsilon ijk, and then I have talked about Cijkl. So this is a first order tensor. First order tensor. This is a second order tensor. This is a third order tensor. This is a fourth order tensor. Now if I have any quantity that is a constant, maybe a, okay, that is a constant, maybe a, so let me write it with red color. No, red has already been used, green is there. So a is a constant, it has no free index, or in other words 0 number of free indices, so it is a 0th order tensor. Clear? And we have the separate names for this. So I mean for some of these, and those names are that this is a vector, okay, and this is nothing but a constant, a numerical constant, okay. But these are tensors, second order, third order and fourth order, okay. So tensor is, I mean, more general than vector, right? So a vector is also a first order tensor, okay. Okay, so I have already introduced to you with the free index, concept of free index, and what are the first order, 0th order, second order and fourth order tensors. So generally from the point of view of mathematics, any parameter that is having k number of free indices will be a kth order tensor, okay. So I think that is explicit from these expressions, but still I am writing for the sake of completeness. So k number of free indices implies kth order tensor, okay, fine, and it is very important. Okay. So now let me talk about something called repeated indices, repeated indices, or it is also called as dummy indices. Okay. So to introduce this, let me talk about the concept of dot product between two vectors, A and B. Okay. So A is having its components as A1 E1 cap plus A2 E2 cap plus A3 E3 cap. Now B is having its components like B1 E1 cap plus B2 E2 cap and B3 E3 cap. So I will suggest you to be acquainted with this E1, E2, E3 cap notations, because in the advanced books of fluid mechanics, heat transfer and all those fluid thermal engineering books, you will be seeing this kind of notations instead of those I, J and K. So I, J and K cap, those notations are generally used in mechanics. Okay. So now everyone can tell that A dot B is a scalar and it is nothing but A1 B1 plus A2 B2 plus A3 B3, right? And also I can write it like this: AK BK from K equals to 1 to 3. Okay. Now we guys are very lazy, and because of that we have omitted this notation, that is summation K equal to 1 to 3, and we write directly this as AK BK. Okay. So now please focus your mind in this lecture, I mean at least for the upcoming 2 sentences, that is, whenever I am writing AKBK, that is K is being repeated in the same expression. So K is being repeated in the same expression, that means it is indicating summation over K, and K can have only 3 values because we are concerned about a coordinate system having 3 independent directions. I am again repeating, please attention, I mean please pay your attention here. So K is repeated in the same expression, K is here twice. That means it is implicitly told that we have a summation sign here over K equals to 1, 2, 3. Okay. Now I am writing this. If you are not clear about this, you cannot proceed about the tensor algebra. So here let me write it, okay, let me write it with the white ink in the blackboard. So if any index is being repeated in an, okay, so let me write the important words with red colors, being repeated in an expression, then it denotes sum over that index, Now I would like to clarify about one word in this sentence, and that is nothing but this word expression. Okay, so expression, I am just giving some examples of this word expression here. So for example, AKBK, AK, AK by BK, AK to the power BK, delta AK, delta BK. Okay, so expressions like this, so this type of expressions are also rare actually. Okay, but expressions like this, mainly multiplication and division and this derivative. Okay, these are called single expressions. So in this expression I have k 2 times, that means it is summation k equals to 1 to 3, it is summation k equals to 1 to 3, it is summation k equals to 1 to 3, it is summation k equals to 1 to 3, it is also the summation k equals to 1 to 3. Okay, so an expression does not mean AK plus BK, AK minus BK. Okay, so here I have two expressions. This is an expression, this is an expression. This is an expression, this is an expression. I am calling this as expression. You can call this, I mean, anything. You can call it a term. Okay, so this is a term, this is a term, this is a term, this is a term, this is a term. But this is not a single term. Okay, so this does not mean that this whole thing is having summation over k equals to 1 to 3. This is not the case. Okay, so please, if you have any doubt or confusion, then please go back into the video and watch this part again. And still, if I am not able to convey you the fact, I mean convey you the concept, then please put a comment in the comment box that, and write that what is your doubt. Okay, I will surely answer. I mean, these parts are main. Okay, I mean, not for this advanced conduction series. I mean, in this point you might be thinking that that what this guy is teaching, I mean, what these things have to do with conduction. So let me tell you that these things are necessary if you are a student of a thermal and fluids engineering, if you are a student of a mechanical design. These things I have already told in my previous videos, you can watch them. Now in fluid mechanics, in the advanced books, you will face these kind of terms in every page of the book almost. Okay, so you will not be able to read those kind of books if you are not clear with this kind of expressions. Okay, okay, so I hope that it is clear that what do we mean by a dummy index. Okay, so now, I mean, why this name repeated index, that is I think clear, because it is being repeated. But why this name dummy index? Now let us see. So purposefully I have written k here in all the terms or expressions, but AKBK is equivalent to writing any other alphabet, maybe AMBM. It is equivalent to AQBQ. it is equivalent to ATBT, anything, because all this expression means A1B1, A2B2 plus A3B3. Okay. So these indices are like dummy. This can be changed to any indices. So whenever in a term an index is being repeated, then that can be changed. I mean, that alphabet can be changed with any other alphabet, that is allowed. Okay, and that is why it is called a dummy index. Okay. Okay. So now let me give you a very good application of this. So if you have studied the fluid mechanics, the concept of fluid acceleration, so the total derivative of velocity is given by del v del t, okay, plus u into or let me write it as, okay, it is okay. Okay, so for the time being, let me just write the x component of acceleration, or it is a1. Okay, so acceleration is a vector, so it is a1, that is the x1 component of acceleration. So let me write it as u1. Okay, so this is u1 plus u2 del u1 del y. So I will be writing instead of y x2, instead of x x1, and it will be u3 u1 x3. If you are not knowing this thing, that is acceleration, the total derivative of the velocity can be written like this, then just accept this one. Okay, so now you see that this part, how can I write this? So this is a term, right? This is a term and this is a term. Okay, so you see here I was having a1 b1 a2 b2 a3 b3, so it is u1 del x1 u2 del x2 u3 del x3. So here in the same expression this index is being repeated. In the same expression this index is being repeated, and in the same expression this index is being repeated. Now take a look on this index. Okay, this is same in all the three expressions. So I can write effectively this as u I del u1 del xi, or I can write this as um del u1 del xm. Same meaning. Now if I have to write the A2 component, okay, A2 component, then for sure it will be del u2 del t, this term, plus in now you can write um del u2 del xm, right? Similarly A3 I can write del u3 del t plus del u3 del xm. This m can be changed with any other alphabet. Okay, now you see this a is a vector, this a is a vector, so I can equivalently write in terms of the initial notation as ai. The moment I write ai, then it becomes del ui del t plus uj del ui del xj. Obviously, instead of this j, you could have written m, k, p, q, r, anything. Okay. So now, see, this expression is a vector. This is a vector. How can you say that this is a vector? I mean, if now you know that it is a vector acceleration, or it has a free index I, but in this whole term, I mean in this whole thing, I have two terms, this one and this one. And notice one thing, that each term is having only one free index. Here also I, here also I. Okay. So it does not matter that each term is having how many how many dummy index, but the number of free index will determine that the parameter is which ordered tensor. So mark my words, I am just writing that number of dummy index does not signify anything, okay, but the number of free index in a term will denote or will decide the order of the tensor. Clear? So in this expression, I have one free index in this term and one free index in this term, and every term in an equation. So this is the whole equation, and this is a term, this is a term, I mean sorry, this is a term and this is also a term. Each term in an equation must have the same free index and same number of free index. So I cannot write here, instead of I cannot write here q and this is I. If this is q, then this has also be q. This has, I mean this has to be q. Okay. So free index in every term in the equation must be same, but the dummy index can be changed. I mean, if I have I could have a separate term, like I can write AIBI is equal to, maybe I have some expression like AIBI is equal to capital AK capital BK plus capital CL plus capital DL. You see, these are the repeated indices, but ultimately this is nothing but summation of AIBI from I equals to 1 to 3. Ultimately this is nothing but summation of AKBK, summation of, I mean k equals to 1 to 3, and it is also the same. So it does not matter if this is I or k or j or m or anything. So dummy indices you can write by any alphabet, but free indices must be same in the whole equation. Okay, these things are very important. Okay, so let me write it here for the sake of completeness. Okay, free index must be the same in all terms or expressions throughout the equation. Okay, throughout the equation. Okay, whereas dummy index has no restriction like that. Clear? Okay. So if it is clear, then my half job is done. Okay. So now let me, okay, another very important rule. Okay, so this is very important. I am writing with 4 stars, very very important. Okay, there cannot be more than 2. Okay, so this should not be the statement. I mean, dummy index, no, that was okay. Any index cannot be repeated more than twice in a term or an expression. So what do we mean by that? That is, if I am writing AI, BI, CI, it is wrong. I mean, there is nothing called AI, BI, CI. So it can denote nothing. Okay, it is mathematically incorrect. Yes, if you write this one, I mean, if you write explicitly AI, BI, CI summation of I from 1 to 3, then it has some meaning. Okay, but in initial notation, summation has nothing to do, and you cannot write AI, BI, CI. You have to write AI, BI, CQ, or I mean, any index can be repeated only twice in an expression. If you repeat that index more than twice, then it has no meaning. It is meaningless. Okay. So this statement is very important, and we will feel the importance of this statement in our near future. Okay. So this thing has some meaning, that is, if I am writing AI, BI, CJ, DJ. Okay, that means in this expression we have a double summation, okay, over I and over J. Okay, AI, BI, CJ, DJ. Okay, remember, you can have multiple dummy indices, but you cannot have same index being repeated more than twice. So these are two dummy indices, and likewise you can have an expression like AI, BI, CQ, DQ, and maybe capital M, capital MJ, capital NJ. Okay, so this expression means we have a triple summation, 1 over I and 1 over Q and 1 over J. Okay, so this is allowed. See, in this expression I have three different dummy indices, but no same index is being repeated more than twice. That is the main thing. Okay. Okay, so now the basics are almost over. Just let me introduce with something called Kronecker delta. Okay. So Kronecker delta. So it is a second order tensor, that is delta ij, and this is equal to 1 when I equal to j is equal to 0 when I not equal to j. Okay. In other words, it is nothing but the identity matrix, because you see, if I write the matrix like this in terms of the delta, it becomes delta 1 1, delta 1 2, delta 1 3, delta 2 1, delta 2 2, delta 2 3, delta 3 1, delta 3 2, delta 3 3. So only the diagonal terms are having the value of 1, all other terms are having value of 0. So it is nothing but the second order identity matrix. Okay. So this was also very important. So I actually planned to complete the whole thing, that is why this K is an isotropic, uh, I mean why K is constant for an isotropic material. I planned that I would complete that thing in this lecture, but I think that will be a very large material for you to digest. Okay. So just let me talk about some more basic concepts, and then I will end today's lecture. Okay. So let us see, for a vector, okay, for a vector, components of the vector changes with the choice of coordinate axis. Okay. So do you agree with it or not? You must agree with it, right? And you can see it actually. If I have a coordinate system like this, so this is my E1 cap and this is x1 direction, this is E2 cap and this is x2 direction, this is E3 cap and this is x3 direction. If I am having a separate coordinate axis, like this, so now my this is E1 dash cap, E2 dash cap and E3 dash cap. So this is x3 dash, x1 dash and x2 dash. Okay. So the same vector, the same vector A, okay, it will be written as ai. Okay, so A will be A1 E1 cap plus A2 E2 cap plus A3 E3 cap, and it is the represent in the, I mean it is the representation in the x1 x2 x3 coordinate system, and the same A vector will be written as A1 dash E1 dash cap plus A2 dash E2 dash cap plus A3 dash E3 dash cap. So it is the representation in x1 dash x2 dash x3 dash coordinate system. So you see that this A vector can actually be written as I mean now you can appreciate this writing, that is a vector can be actually written as ai ei cap, right, or it is the same as aj dash ej dash cap, I mean ej dash cap, okay, that is true, right, because I mean now I think you can appreciate this. I mean this is summation over I from 1 to 3, so this is the these three terms, and this is also summation over j 1 to 3, and these are these three terms. Okay, so you see that in this purple coordinate axis the vector is indicated through this aj dash, and in this green coordinate axis it is indicated by this ai only. Okay, now my next question will be that uh, can we derive uh, a mathematical expression between ai and aji, I mean aji, obviously it should be aji, AGI not AI dash, sorry. Now why it is not AJ dash? Because I need to correlate between A1 and A1 dash, A2 and A2 dash, A3 and A3 dash. The corresponding x, I mean the x component of the green coordinate axis, I have to correlate this with the x component of the purple coordinate axis, not with the y component or the z component. The moment I change this I as j, okay, then it is a different free index. Okay, that is why it is ai dash, not aj dash. Okay, so should I conclude this lecture or? Okay, so let me conclude this lecture here, because I would like you to go through all these materials once again, and after going through all these things, if you have any doubt, any new doubt that I have not covered in this lecture, maybe I have missed something, then you put that in the comment box, then I will cover that in the next lecture as the extension of the basics. Then I will go through the main thing, that is why the thermal conductivity tensor boils down to a constant for an isotropic material. Okay, so I will complete that for sure in the next lecture, and before that please be acquainted with these concepts. Okay, so until that, goodbye and take care. Thank you.